Hello, we're Team Prosthetics, and our design is a prosthetic redesign. So, some background information. Bert Paul, an above-the-knee amputee, struggles to keep his prosthetic secure while playing golf. He has a residual limb that has an irregular shape due to the uh, uneven amputation, creating air pockets inside the prosthetic where sweat pools, causing discomfort and slippage for his prosthetic. Limited dexterity requires an intuitive, low-effort solution to his prosthetic stability issues. Amputees typically use a silicone liner as the interface between the socket and the residual limbs, and they add sock layers for additional comfort and a better fit. Attachment methods are one of the three, usually. The first one being mechanical suspension systems, such as a strap or a belt to help secure it in place. Second one is vacuum pumps with continuous suction, and a third one is a natural negative pressure suction, which is the method that Bert currently uses. Our customer identification, our main customers are Bert Paul and any other amputees dealing with a similar issue. Customer needs are removing sweat buildup, working solution that is not bulky and is easy to use. Customer demands. So we sat down with Bert and he listed his main goals in our design, and he said, I want the leg to function with the least amount of issues. For me, it's about the ease of removing sweat without losing suction and having to take my leg off. And there are times where my leg falls off and I can't get it to suction back on, and it's embarrassing.
Yeah, looking at our problem statement, the main problem that Bert struggles with is suction and sweat buildup. So the current solutions that are in place right now either require manual effort, which might be difficult for someone with low dexterity, such as Bert. So we're looking at a low maintenance automated method that we're looking to develop that will maintain suction and maintain balance of the system. So some of the design requirements we came up with is obviously removing sweat buildup from the socket. We need to do this without losing suction and without having the need to have the prosthetic be removed and then reattached again. We want him to be able to use it while in activities where he will be sweating the most. And we want our solution to be small, and we don't want it to be permanently attached to the socket. So looking a little bit deeper into our requirements, it has to be able to unattach and attach, like I said. It should have a minimal footprint on his socket. It should be able to be used by low dexterity users such as Bert. It can't cost a lot. It has to be very light so that it doesn't impact his balance or mobility. The battery life has to be able to have our solution be used for multiple cycles and that doesn't have to be recharged too often. The sweat reservoir has to have large enough capacity to not overflow, and it must drain sweat in a reasonable time. So moving these requirements into benchmarks, we desire the ease of use to be over a 75 SUS score, which is a score that like a feedback score based on survey. We want it to be less than $700 as our budget. The mass has to be light and it has to be less than 5 pounds. The capacity of our reservoir is greater than half a cup. The speed to drain has to be around 2 milliliters per second. And then the battery life has to be more than 30 minutes. So looking at our design process as a whole throughout the semester, we started out with a liner redesign. And this was basically trying to prevent sweat rather than get rid of sweat after he already sweated, obviously. And so that was our kind of first step. And obviously, this is not the direction we went with.
So after we came up with that first initial design, we decided to interview and learn more about the prosthetic process. And so we reached out to Joe Pongratz at Pongratz Orthotics and Prosthetics. And during our discussion, we learned a few key things about the process and technological aspects about prosthetics. One thing was that the cooling liner that we had thought of already existed on the market. And one of the things that we never considered initially was weight. Prosthetics users require significantly more energy to operate their prosthetics. And for someone like Bert, who has an above knee prosthetic, that number can be anywhere from like 3 to 4 times the amount of energy. We also learned that suction based attachment may not be the best, and we learned about the various mechanical options for that. And ultimately came away with the realization that redesigning our liner wouldn't really solve the problem that we faced. And so after that, we came together as a team, had a discussion, and realized that our main problems that we needed to address were making sure that the prosthetic fit, making sure that there's still space within the prosthetic for Bert's leg to move around, and lastly, making sure that we identify what the actual problem was. And in doing this, we kind of had to decide, do we want to create a solution that only works for Bert or for general prosthetics users? You can kind of see some of the questions we had there, but basically, before we could really decide what we were going to do, we had to interview Bert. So, as a team, we met with Bert and came to learn the following facts. First was that Bert's amputation is unique. The angle that it was amputated at was not the norm, and so that causes issues within his prosthetic that other people don't experience. Because of that, other solutions aren't as effective on him or just cause pain. And so, unfortunately, while there may be a lot of solutions, Bert relies on insurance to cover these. And so these prosthetics are already expensive, but these even more high tech solutions just cost more and more money. And so his insurance won't pay for that. So we had to keep the solution very cheap. Um, Onto the actual mechanics of the slipping, we learned that the sweat pulls up in the cavity between the socket and the liner, and usually results in a suction loss within about 1 to 2 hours of playing golf. Bert mentioned that he usually has about a quarter of a cup of sweat in the socket by the time it slips off, and one of the things that we noticed was that he also had limited dexterity due to his surgeries and age. And so, because of that, as a team, we came together and decided to change our design to remove the sweat from the socket without having to remove the socket. We had to make it easy to use with low dexterity. We had to minimize the weight and cost, all while keeping the suction between the liner and the socket. And so that brought us to two concept designs. Our first design was an automatic pump module that we would attach onto the socket, and it would use sensors to detect sweat and humidity and automatically pump it out into an attached little detachable container. The other option was a little manually operated pump that you just insert into the socket, manually pump, and then that would pull the sweat out of the socket into another little container.
So comparing those two, the automatic pump and the handheld, we have some pros and cons here. So for the automatic pump, the pros are there'd be no action needed, minimal maintenance, low dexterity needed, maintains suction, and has a container to safely store and dispose of the sweat. Cons are it's bulky, it's going to be bigger, it's always attached, and modifying the prosthetics is out of our budget. As we said, prosthetics are very expensive, and the last thing we want to do is be modifying those and something goes wrong. And it needs a battery to power sensors in the pump. For the handheld, the pros are it's easily detachable, removes sweat as needed, very simple design, requires no power, and has a container to safely store and dispose of the sweat. The cons are is that it could weaken suction when removing the sweat. It requires a manual input. It requires user to feel the sweat in the socket, and the suction is not as strong as the actual pump. So after comparing the two designs, we chose the automatic pump, but we made some changes to go along with it. So the design has a removable casing that attaches onto the prosthetic using magnets. Since Bert mentioned his ability to feel the sweat buildup, we removed the sensors for longer battery life and retain strong suction from the pump in a container for the sweat to get stored in, and it only requires a simple on-off switch to operate. And there is a exploded view showing our different components, the housing shell, the valve adapter, everything that would go into the housing shell, the on-off switch there, and then the lid that would encase everything into the shell. Then our bill of materials, everything that does not have a material listed on it is something that we will buy ourselves either off of Amazon or eBay. And everything with the PETG material is something that we plan on 3D printing.
So after our whole design pivot, we went back to our decision matrix to ensure that the new automatic pump uh, was our best design that we could come up with. So we compared it against our original concept, which was the liner, the automatic pump, and the handheld pump idea. And we based it off the following criteria: the ease of use, cost of resources, mobility, comfortability, sweat removal speed, battery life, and aesthetic. And we weight them against certain different percentage weights as well as if they are mandatory or not. Then we weighed with a scale from three being the easiest to use, one to the hardest to use. And after weighing each criteria to their concepts, it showed that our new automatic pump design was the best decision. Looking here, we have our functional block diagram. And so this really just shows exactly what we expect to happen from the initial situation in the top left, where Bert's sweat falls over the liner and pools in the socket. This happens because of the poor fitment of the liner, it leads to air gaps. So the sweat actually is trapped in the gaps between the liner and the socket. Bert feels the sweat buildup in his socket, and it goes to activate the pump with this via the switch. After the pump is turned on, it will drain the collected sweat to the internal reservoir inside of the housing. And best case scenario, the sweat is removed and the prosthetic is secured. The way that we plan to do all this is shown here with our component functional block diagram. And so this breaks down the process into each of the components. Top left, we see the test socket, where we're going to use a test liner and an RTH sensor, that is a temperature and humidity sensor. And that sensor will be connected to our testing electronics module, which uses an Arduino board, an LED array, and a battery. And so that will help us see what conditions are going on inside of the socket and seeing the conditions that the pump is actually working through. We have our 3D printed valve adapter using the existing air relief valve and a pump attachment valve, which connects via polyurethane tubing to the pump. And inside of the pump housing is super basic. It's just a pump and on-off switch, a battery, and not shown here as a breadboard. We're still on the fence about using the breadboard or not. And from there, we're going to take the water or the sweat from the pump into either the environment or the internal sweat reservoir.
All right, and moving in further detail into our pump selection, as you can see, there's a company called Welco that offers a different selection of these peristaltic pumps, and we are choosing the smallest option, which is the WPM, and it offers a maximum flow rate of 120 milliliters per minute. And the reason that we're going with this pump is because at the end of the day, there's not that much sweat present. It's only about a quarter cup, and the pump will be active before the max limit is reached. And even if you consider a quarter cup at 120 milliliters per minute, it's the smallest option, but it's going to be able to drain that within 30 seconds, which is if Bert is able to feel the sweat pool up, he's going to turn it on before that quarter cup volume is even reached. And then as you can see, we also did a weight analysis. And so the original prosthetic leg that we are testing with weighs about 10.5 pounds. And just doing a quick, summation of all of the components that we're, going to add for our final solution, you can see that, with our attachments, the total leg will be 12, almost 13 pounds. And the total weight of our attachments are like about 2.3 pounds. And the percentage of the original weight is I guess 18%. But that meets our 20% or lower criteria. And yeah, this will, we want to keep our solution lightweight because these prosthetic legs are already, very difficult for the user to move. So any added weight really just adds to that. And it's the best idea to keep it lightweight. And then, just going with that Welco WPM at 120 milliliters per minute, we calculated our runtime. Runtime is about 30 seconds. And inside of our housing, we'll be using a 2600 milliamp hour battery. And at the required amperage of the pump, which is 250 milliamp maximum, it actually turns out that we can run the pump for 10.5 hours off that battery and just over 1,000 drainage cycles, which is pretty impressive for such a small battery and pump. And then over the course of the semester, our team has concluded that sweat buildup is the primary cause for suction loss and discomfort. Like we said, that was mainly just talking to Bert and a lot of research into prosthetics. This is a very common issue for a lot of prosthetic users, and it seems that sweat reduction solutions are going to be feasible as it meets all of our requirements. And because of dexterity issues, an automatic solution that can just be operated with a switch seems like it's going to be our best option. Um, for future recommendations, we want to match the housing of our housing of our components exactly to the contours of Bert's current socket, and that's just going to help us get a good fitment and basically optimize our design to keep it small and lightweight. And yeah, we're just going to continue to do iterative testing with Bert, and that's one of the big focuses next semester is to try and get our prototypes out quick enough that way we can have some time to test with Bert.
Taking in a look at what we've done so far and what we plan to do next semester. This semester, we've completed our project initiation phase as well as the background research phase. We've also worked through our conceptual design where we've put together design models and sensor developments and other benchmark things that we can put our initial designs together with. We've wrapped up our R&D phase with the preliminary design presentation we're doing right now. This was primarily completing CAD modeling and FMEA analysis, sorry, of our design to make sure it would be mechanically sound. This also was complete with initial budgets that we'll look at later. Next semester, we're going to look at our prototyping and final product phases. This will be where we put together our initial prototypes, test it, iterate it based off any changes we deem needed, and then do that again and again until we get down our final product, and then we will have our presentation. Looking at our budget, we're looking at around $250, so we're well within our restrictions. The bulk of that is going into our structural components, which is the 3D printing filament, as well as our plumbing components. We have a lot of tubing and connectors that go into the plumbing connections that we hope to use. We also have the electronics that make it automated. So with a switch, with a flip of a switch, it can be automated and ease of use for the customer. And then we have a small amount going towards our testing, which is our Arduino and our temperature and humidity sensor, which will go into validating it with the benchmarks we've set for ourselves. Thank you so much.